Have you ever gazed up at the night sky and wondered about the secrets it holds? Get ready to embark on an exhilarating adventure beyond the stars, where the mysteries of the cosmos await. In today's captivating exploration, we're delving into the realm of space science like never before. From the mesmerizing birth of stars to the mind-bending possibilities of exotic celestial objects, prepare to be dazzled by the wonders of the universe. Join us as we uncover the awe-inspiring phenomena that shape the cosmos, from the dazzling light shows of thermonuclear reactions to the breathtaking dance of celestial bodies in the vastness of space. But that's not all. We'll also unravel the enigmatic nature of hypothetical stars, including those that defy our imagination by being composed of pure vacuum. So, fellow cosmic enthusiasts, buckle up and get ready to expand your horizons as we journey through the captivating wonders of space. Don't forget to engage with us in the comments below with your thoughts, questions, and cosmic curiosities. Some of these stars can mimic black holes and resemble dark energy, which is why they have been the subject of many recent studies and even some sensational drama in the world of physics. In this video, we're going to explore all of it, from the physical theories at the core of these ideas to the wildest speculations surrounding them. First, we need to lay some groundwork and understand how stars work in general, starting with the most important star of all, the Sun. Since the Sun is made of gas and not solid matter, you couldn't stand on its surface like you would on the Earth. The Sun's gravity would just pull you down toward the center. So why doesn't the gas at the surface get pulled inwards too? It turns out that there is a pressure pushing outward from the Sun's core that counterbalances this pull of gravity. The main source of this pressure is the radiation created by fusion reactions in the core, the same radiation responsible for carrying light and heat from the Sun to the Earth. Whether you think of radiation as individual photons or waves in the electromagnetic field, its path from the core toward the outer layers of the Sun will cause an outward push in all directions. This radiation pressure wouldn't be enough to stop you from falling into the Sun, but it's just enough to stop the Sun's own gas, which is relatively light, from collapsing in on itself. This balancing act between inward pulling gravity and outward pushing pressure is a feature of pretty much all known types of stars. What differentiates different types of stars is where that pressure comes from. For our Sun, the pressure comes from fusing hydrogen into helium. When the Sun runs out of hydrogen in about 5 billion years, it will become a red giant star, whose pressure comes from fusing helium into even heavier nuclei. Eventually, the Sun will also run out of helium and any other light elements that could be used as fuel for nuclear fusion. At that point, it will collapse into a small star known as a white dwarf. Since no more fusion is occurring anymore, white dwarfs are sometimes called stellar remnants instead of stars. But if there's no more fusion, where does the pressure to support these stellar remnants come from? It turns out that gravity pulls the gas of a white dwarf inward until it's so dense that a new type of pressure emerges, known as electron degeneracy pressure. This is a purely quantum mechanical effect, and it's the same effect that's responsible for you not being able to pass your hand through solid objects. Electrons simply cannot get too close to each other without an extraordinary amount of energy. But some stellar remnants are so massive that even electron degeneracy pressure isn't strong enough to counteract the pull of gravity. This is called the Chandrasekhar limit. It's absolutely impossible to have a stable white dwarf any heavier than 1.4 times the mass of the Sun. If a star has burned through all its nuclear fuel and its core is still heavier than the Chandrasekhar limit, that core will collapse in on itself until it becomes so dense that an even stronger type of quantum pressure emerges, known as neutron degeneracy pressure, which, as you may have guessed, prevents neurons from getting too close to each other. A star that reaches this state is called a neutron star, the smallest and densest known class of stellar objects. So now you might be wondering, is there a maximum mass that a neutron star can have while still being supported by neutron degeneracy pressure? And there is. This time, it's about 2.2 times the mass of the Sun. Any heavier than that, and the neutron star would keep collapsing under the influence of its own gravity until, well, actually, not until anything. As far as we know, neutron degeneracy pressure is the strongest possible pressure that ordinary matter can exert, so there's nothing left to prevent a sufficiently heavy stellar remnant from collapsing in on itself forever. This is the fate that might await some of the most massive stars we've observed in the universe. From the perspective of an outside observer, these stars would get so dense that all we'd be able to see is a black hole. But then scientists started to wonder, what would happen to a star that wasn't made of ordinary matter? If exotic forms of matter could hypothetically produce even larger pressures than neutron degeneracy pressure, then what new kinds of stars could exist? You might think that we could just continue the pattern that we were starting to see earlier. Stars could get even smaller and even denser than neutron stars as long as they were supported by some even greater pressure. You might think that the only limit on how small these stars could get would be the point of no return, where they would turn into black holes. That point of no return is when a star becomes smaller than its own Schwarzschild radius. This is almost true, but not quite. Instead, physicist Hans Adolf Buchdahl showed in 1959 that a star made of any realistic form of matter with positive energy density and pressure can't be smaller than 9-8 times its Schwarzschild radius. It might not sound like a big difference, but that factor of 9-8 means that any realistic star has to be noticeably larger than a black hole, making it much easier to tell them apart. That's when physicists began asking about stars that Buchdahl would call less realistic. Wow, what a mind-bending journey through the mysteries of space. As we've delved into the fascinating realm of exotic stars and their mind-boggling properties, one thing's for sure: the universe never ceases to amaze. But hold on to your cosmic hats, fellow space enthusiasts, because our adventure doesn't end here. There's a galaxy of knowledge waiting to be uncovered, and our channel is your ticket to the stars. By staying connected with us, you'll dive deeper into the wonders of space science, unlocking secrets and unraveling the enigma of the cosmos one video at a time. So don't miss out on another stellar discovery. Hit that subscribe button and join our community of cosmic explorers.